cumulative distribution function. So like check this example. Let x be and y be two random variable with joint probability mass function. Probability density function is given by this: f of x y is equals to e raised to power minus x plus y. When x is lying in the domain x greater than 0 less than infinity, and y lies between 0 to infinity, and it is 0 otherwise. So, like, if this is the density function and someone told you to find its cumulative distribution function, that is this one, and you know that we can calculate joint cumulative distribution function with the help of joint density function using this formula for the case of continuous random variable. So here we will know that here since xy belongs to R2, R cross R, so it means we have a two-dimensional plane as a domain. So we consider like first region in which x is less than 0 and y is anything from minus infinity to plus infinity. So if x is less than 0, it means our this definition will give you this. And since here x is less than 0, x is less than 0 means x is less than 0 means this domain. It is lying in this domain. So if it is lying in this domain, then it is having 0 value. So whether y is from lying from minus infinity to plus infinity, but since x is less than 0, so for whatever x is from minus infinity to x and x itself less than 0, so it means the definition of fxy will give us 0, and so this will be 0, and if it is 0, then this whole integration is 0. Now, if x is greater than minus infinity and less than plus infinity, and y is less than 0, so x can be anything and y is less than 0. In that case, again, it lies in this because when we are taking v from minus infinity to y, you have to write the value of this. But this v is taking value from minus infinity to y, and y itself less than 0. So for any value of y, they are also less than 0, and for less than 0, f of x y is 0. So here you are again getting 0. Now you take another domain which x lies between 0 to infinity, and so that you are covering your whole domain. So now x is greater than 0 and less than infinity, and y is greater than 0 and less than infinity. So then you have used this. Now your v is going from minus infinity to x, u is going from minus infinity to x, and v is going minus infinity to y. And you have to substitute this value. But you know that the definition here x and y are greater than 0, but the limit of integration is from minus infinity to x. So it means that this can be divided into two parts, like minus infinity to 0 and then 0 to x. Similarly, this can also be defined like minus infinity to 0 and 0 to y. But the part in which we are talking about minus infinity to 0, again the definition of this fxy is 0. So this can be rewritten as from 0 to x, and v goes to 0 to y, and then in that domain when v is greater than 0 and less than infinity, so v is greater than having values from 0 to x, and x itself is greater than 0. Similarly, v going from 0 to y, and y is itself greater than 0, so both x and y are greater than 0 here. So it means whatever the domain of integration is considered here, in this domain uv is greater than 0. And if both f, u and v are greater than 0, then we use this definition. And if we substitute this definition, we will get this one. Then we can write this as e raised to power minus u into e raised to power minus v. And then we are integrating here with respect to v plus v variable, then we know that it is e raised to power minus v upon minus 1, and the limit of integration y. And when you substitute, you will get e raised to power minus y plus 1. For y, you will get e raised minus e raised to power minus 5. For 0, you will get plus 1. And then this is actually part which is like not containing any u. So this will be outside of the integration, and integration of e raised to power u is minus e raised to power u upon minus 1, and then you substitute x equal to 0 and x, then you will get this one. And finally you can write like this. So like other domain you have written here 0, like when x is less than 0 or y is less than 0, and when both of them are greater than 0 and less than infinity, we have this as so it is 1 minus e raised to power minus y like this. So this is the way you calculate joint cumulative distribution function from joint probability density function. Like in this above case, we can also calculate marginal density function of x. So marginal density function is like this is the definition or formula for calculating the marginal density function from the joint. This is joint density function, and this is marginal density function for random variable capital X. And when we are calculating marginal from joint, like we are calculating for x, then we integrate to this for y from minus infinity to plus infinity dy. So this should be dy. Then f of x, y, x, y, that this is the definition of the density function in this case. And then we try to find what is the value of this integration. So we take first y goes to minus infinity to 0. And we know that when y is lies between minus infinity to 0, then f of x and y is having 0 value. So we are substituting 0. Another domain of integration is 0 to infinity, and in this domain we have e raised to power minus x plus y as the definition of f of x y. And then since we are integrating with respect to y, so e raised to power minus x will be outside, and integration of e raised to power y is this one. And then when you substitute y equal to plus infinity, you will get 0. And when you substitute y equal to 0, you will get 1. And then this is your this probability density function or marginal density function of the random variable x. So like here someone like if you want to calculate that when this x is less than 0. So if x is less than 0, you know that this f of xy is 0. So in that case f of x is 0, because if x is less than 0, then this value is 0 from the definition this. So it is 0, so it means f of x is 0 if x is less than 0. And for x greater than 0 and less than infinity, we have already solved here. Like if x is greater than 0 and less than infinity, then we have to do all this calculation. It means it is the case when x is greater than it is the case like when x is greater than 0 and less than infinity, because you are calculating density function for the random variable x, then you have to specify its values for all x lies between minus infinity to plus infinity. So for minus infinity to 0, it is 0, and for x greater than 0 and less than infinity, it is having value e raised to power minus x. So after this calculation, we are having this one as a marginal density function of x. Similarly, you can calculate marginal density function of y also. There is another problem that x and y be jointly distributed random variable with a joint density function given by this. So here you can see that the definition of the joint density function of the two random variable x and y is given like this: 2 when x is greater than 0, and this x should be less than y also. So this condition will also be true, and this y is finally less than x. If these conditions are true, then it is having two value, and otherwise it is having zero value. So now you have to find the marginal density function of x, marginal density function of y. So how you calculate that one? So you know that to calculate density function or marginal density function of x, you have to integrate this joint density function with respect to y within the limit minus infinity to plus infinity. So you split this limit of integration into three parts. So one is minus infinity to x, another one is x to 1, and another one is this another one is this y goes to 1 to x infinity. So why he split it like that? Because you have to integrate from minus infinity to plus infinity. In this domain, the value of fxy, because you can see now here y is moving from minus infinity to x, it means y always remain less than x in this domain. So if y is remain less than x in this domain, so the value of this f of y x y is 0. From this definition, you can write a place of this 0. Then you write x to 1. So if your y is lies greater than x and less than 1, the value of this function is 2. So here you write 2. Now when y is greater than 1, then it again goes to otherwise case. And otherwise case, so this part is also 0. So only in this domain, we are having value of fxy as 2. So we will see. So like first domain integration is 0, this is also 0, and in this domain we are having 2, and the integration of 2 with respect to y is y, and lower limit and upper limit substituted after this integration, we will get 2 minus 2x. So this is the case like we have discussed for x greater than 0. Like if I am taking my axis, if might take this split is actually for x is greater than 0 we are discussing. If suppose x is less than 0, this. So if x is less than 0, it means this is actually 0 because it again goes to otherwise case, and finally you are getting 0 if your x is less than 0, because it goes to otherwise case, you directly value substitute its value, because for x less than 0 it is having 0 whatever may be the value of y, so it remains 0, so it is 0 and integration is also 0. And for x greater than 0, you are having this, then less than 1. For x greater than 0 and less than 1 also, because this is the domain. If x is greater than 1, it is again 0. So this is the marginal density function of x. Now, like marginal density function of y. So the marginal, to calculate this marginal density function of y, we are again taking this one, because we are calculating marginal density function from joint density function. So we have to integrate with respect to the variable x within the domain minus infinity to plus infinity. And again, our condition is like that. This is having the function joint density function is defined like it's 2 when x is greater than 0, less than y, less than 1, and it is 0 otherwise case. So now we are integrating with respect to x. So we have taken one limit from x goes to minus infinity to 0. Another one, again we are taking here the case when x is less than 1, sorry. Here we are discussing when y is greater than 0 and less than 1 case. Otherwise domain it will give us 0. Okay. So in this case, if y is greater than 0 and less than 1, then we are trying to calculate what is the joint value, this fxy, x comma y. So, and now we are integrating with respect to x from minus infinity to plus infinity. So when x is minus infinity to 0, it is having some, or 0 to y, it is having some, and from y to infinity, it is having something. Even though he has to write here 1, because it is not going till infinity. So this part, because x is having value minus infinity to 0, this is having 0. For 0 to y, because this part 0 to y, it means it belongs to this domain. Here x is less than y, so it in this domain it is having two values. Now x equals to y to infinity. So it means here in this part of the integration, x is having value greater than y. And if x is having value greater than y, it belongs to the other domain. Other domain means 0. So this value is also 0. Because here we have a condition that this x should be greater than 0 and less than y, then only it is having two values. So here x is greater than 0 and less than y. So, but here if with this limit of integration, x is taking value from y to infinity. It means x is taking value more than y, so it is 0, it is 2, and then we will write like this. 2 value and then its integration is 2x, then lower and upper limit after substitution you will get 2y. So this is the way we calculate our this marginal density function from the joint density functions. So like we have learned here, uh, hmm, that we have, if we are having two random variables like a capital X and capital Y, then we are having this joint distribution, joint densities, joint probability mass function, and like this. So, like if we are having this, how this conditional probability concept to generalize to these random variables. So, let's first talk about like conditional distribution for the case of the discrete kind of random variable. Okay. So let x and y be a two discrete kind of random variable with the joint probability mass function. So joint probability mass function, it means this. This we call the joint probability mass function. Okay. The probability that x equal to xi, y equal to yj. Or I denote in my notes like pij, but actually this notation, this one is termed as a joint probability mass function. For I goes to 1 to infinity and j goes to 1 to infinity. So here the range set of x is these x1, x2, something up to infinity. Similarly, ry is y1, y2 up to infinity. So this is our mm, joint mm, probability mass function. So now if I want to know what is this conditional probability mass function. So the conditional probability mass function for a given y equal to yi. So this is actually we want to know. So what way I will write like a probability that capital X equal to xi given y equal to yj. And if you remember the definition of probability of A given B, probability of A given B is probability of A intersection B divided by probability of B, provided probability of B is not equal to 0. Okay. So here like one event is like we have to calculate probability that what is value of x equal to xi given y equal to yj. So for that we use the definition of conditional probability, and it is like probability of A, and you know that this comma is actually representing the intersection of these two events. So probability of A intersection probability of B divided by probability of B. So this is the way we generate the conditional probability distributions. So like similarly, like someone wants to know the probability of y given y equal to yj for given x equal to xi. So again, it is A intersection B divided by probability of B. Here for B is x equals to xi. So these are known as the conditional probability mass function. This is conditional probability mass function. This is also conditional probability mass function, and this one is a joint probability mass function of x and y. And this one marginal probability function mass function of y, and this one is marginal probability mass function of x. Similarly, we have the concept for this density function also. So let x and y be two continuous random variable with joint probability density function f of xy. So this is the joint density function. Then the conditional density function of x for a given y equal to y is defined by this notation. F x, this vertical line that is conditional. So this is the notation is used to define conditional density function. So x conditional y. So like earlier it is like this f x x. So now we are writing f x given y equal to small y, or x given y equal to small y. So this is the conditional density function. So of x when it is given that y equal to small y. So it is how it is written that fxy that is this joint density function of xy divided by marginal density function of y at small y. Similarly, the conditional density function of y given x equals to small x, that is this one. So this is also like a joint density function of xy divided by marginal density function of x at the point small x. So this is like f y, because now we are conditioning x equals to small x, and y is a variable here, and x equals to small. So this is the conditional distribution of y when it is given that x equals to small x. So and the notation is this one, y conditional x, which is x conditional y. So y conditional x, this means joint density function of x and y divided by marginal of x, which is y given x, and x given y, joint density function of x and y divided by marginal function of y. So this is the way we define conditional probability mass function and conditional probability density function. Now we talk about this conditional distribution function or conditional cumulative distribution function. Earlier you know that f x, this is the notation we use to represent the distribution function of x. Now we use this notation that to represent this conditional, like f x given y equal to y, it is given, and then small x given capital Y small y. So this is the conditional distribution function of the random variable x when it is given that capital Y is equals to small y. So it is like integration, because earlier also we are integrating with from minus infinity to x, and here we are having earlier the density function of x. Instead of that, we are having conditional density function of x, and we are to integrate with respect to u from minus infinity to u, x given y, u given y equal to y. So this is called the conditional distribution function of x for given y, capital Y equal to small y. This we have already discussed. Or sometimes it is like if they, instead of writing this is actually, because the definition of conditional distribution of x given y equal to small y is this one. So we directly having this here. Some author may use this like also. This conditional distribution function of y given x equals to small x. So here also the same thing, like b is integrating from minus infinity to y dv, x equals to small x is fixed, and this variable b is moving, and this is y. And the definition of this one is this one, conditional from the density function of y given capital X equal to x small x is given by this one. So we substitute this value here and then integrate minus infinity to y, and then we will get our conditional this distribution functions. Okay. So like we have already solved one example, and in that example we are having that the definition, if you remember, the definition is this one. Okay. This is the definition. Actually, this is not the definition. If you remember that this is the problem. This is kind of definition we are having: x greater than 0, less than y, less than 1, and 0 otherwise. Okay. So this is the giant density function is given in earlier example, and we have to find the conditional density function of x given as f x x given y equal to small y. So it is like given y equal to small y, and you know that it is the definition. Then joint density function of x divided by conditional, and the conditional we have to because y is already given here, so this x cannot go beyond y, so we have to put the limit from 0 to y only because y is already given, and this is the value of f of xy2 already given, so this 2, and fyy we have already calculated this marginal density function of y for a given y, and here y is a small y, so we have substituted this in the marginal density function. So if x lies between 0 to y, the conditional density function of x when y is equal to small y is given by this, and otherwise it is 0. So this is the way we calculate our conditional density function from giant density function, and this marginal density functions of y. So like that we can also solve for this x also, that conditional function density function of y for a given x. Then so this is actually, you have to remember this result. If x and y are two independent random variable, if x and y are two independent random variable, you have to remember this thing independent because we are going to use it many times now. So if you know that two random variable x and y are independent, then their joint density is equals to the product of their density for the independent random variable only, not for all. Similarly, joint distribution function is the product of joint joint distribution function, and probability of this event is equals to the product of probability of this event into the probability of this event. So similarly, like here I had written only for this discrete for the okay. This here it written for this. This is written for continuous, and this is like a probability mass function. You can interpret also like that because probability of x equals to xi comma y equal to yj is a joint probability mass function, and it is given that x and y are independent. So intersection of these two events is actually probability of x equals to xi into probability of y equal to yg. Now we calculate the expectation of function of two random variables. So earlier we have calculated like x is a random variable, then we have calculated a g expectation of gx, and expectation of gx is like if x is a continuous, it is g of small x and then into density function of capital X and integration within the domain minus infinity to plus infinity. Similarly, if x is a discrete kind of random variable with probability mass function probability capital X equal to small xi, in that case also we can know the formula. But here, like if we are having x and y as a two random variable and h of xy is a function of these two random variables, then this is becomes another random variable x of xy, and what is the density function expectation of this one. So the expectation of this one is given by this, because we know that x and y are already jointly distributed with this joint density function. So we write h of xy for small xy are the value taken by the random variable capital X and capital Y into the joint density function. Earlier we are integrating only with respect to x because it's a joint density function, so we have to integrate with respect to x from minus infinity to plus infinity, with respect to y also minus infinity to plus infinity, and whatever value we are getting here, that will be the expectation of the function of the two random variables x and y. So this is formula for the case of when x and y are continuous kind of random variable. If they are discrete, like if they are discrete, then this joint density function is replaced by joint probability mass function. This one you can see, and this h of xy is replaced by the values at xi and yj, because in that case the random variable capital X and the capital Y are taking discrete values xi and yj, and the probabilities at this, that is joint probability mass function at xi and yj, and instead of integration we have to take two summation, and the summation range over all values of xi and all values of yj, and whatever this sum is come, this is known as the expectation of the two discrete kind of random variable x and y. Now, if x and y are independent random variable, so if x and y are independent random variable, either discrete or complex or continuous, then expectation of xy is actually product of their expectation. So it means expectation of x into y is actually expectation of x into expectation of y. So we will prove this one, like for the case we are assuming that x and y are continuous kind of random variable. And it is xy, we can think like x h of xy. It is a function of two random variable x and y and defined like this. H capital X comma y is x into y. So like, and then we know that earlier definition that we have to integrate with respect to x minus infinity to plus infinity, with respect to y minus infinity to plus infinity, and h of xy for the small x and small y, and it is like small x into y, and it is multiplied by the this joint density function of x and y. But here it is given that x and y are independent. So if x and y are independent, then their joint density function, this one, actually the product of their density function. So this thing can be replaced by this. And then here limits of the integration are constant, so you can change the order of integration also. So if you change the order of integration, you will get this minus y goes to minus infinity to plus infinity y fy y dy, and other things are there fx, fx and dx. So if you remember the definition of expectation for the case of single random variable, so it is given by this, like y is the small y is the value taken by the random variable capital Y. It is the density function of the random variable capital Y. and we are integrating in the whole domain minus infinity to plus infinity, it means the result of this integration is actually expectation of y. So we have substituted its value. So after integration, this becomes like a constant, so it will be out of this integration. And now we have this x goes to minus infinity to plus infinity, and x fx dx. Again, if you remember the definition of the expectation for the random variable x, it is like the value taken by the random variable capital X, and f of x is the density function, and you are integrating from minus infinity to plus infinity, so it will be the expectation of x. So you have proved that if x and y are continuous kind of kind of random variable, then the product of the expectation of xy is equals to expectation of x into expectation of y. And similarly, you can prove this result for the case of discrete kind of random variable. Okay, so you try yourself that one. Now we try to find what is the expectation of xy, x plus y. So we have already calculated expectation of x into y for the case when x and y are independent. But in this problem, we are not assuming x and y are independent. It means they are two general random variable and we don't know about them whether they are independent or not. So this result is true for any kind of random variable, and the earlier result is true for only the case of when you are having independent kind of random variable. So we'll see. We know that this x plus y is also function of x and y. So here hxy is like this one, x plus y. So we have written, and that this is the joint density function of xy. So this is the expectation of x plus y. We have to integrate with respect to x minus infinity to plus infinity with respect to y into h of xy. Okay, good. Okay, okay. We'll meet tomorrow.
So I need some of the seniors who are doing my senior scholars, but I couldn't meet anyone from this fourth or second semester.
Okay, we will discuss tomorrow. Right now, I'm taking class. Okay, so here this is the joint density function of x and y. Okay, so from the properties of integration, you know that integration is having linearity property. So you can write like this. Okay, instead of this small result, we are proving one more generalized result here. So here only x plus y. So here we have multiplied a into b, y, and c. So if c equal to 0, a equal to 1, b equal to 1, this will become this result. So instead of this going limited case, we are going more to provide two more generalized result. This is that if x and y are two random variable of continuous type and abc are three real constant, then expectation of ax plus by plus c is equals to a expectation of x, b expectation of y, and plus c. So this we have to prove. For the sake, we have assumed that x and y are two continuous kind of random variable, and this thing ax plus by plus c is a function of two random variable x and y like h x comma y. So if we replace here x by small x and y by small y, we will get this h of small x comma small y, and then we have to multiply the joint density function of xy, and we have to integrate with respect to x and y within the limit minus infinity to plus infinity for x as well as for y also. And then we use the linearity property of integration. This because this is plus, so we can split like a small x like this, and then plus b y because y is a is constant and y is a heavy. You cannot go outside of this integration, and c. So this can be rewritten like this by using the property linearity property of integrations. So here in this above case, you can see what is the value of this one. Here it is joint density function of the two random variable x and y, and you are integrating this joint density function with respect to the whole domain. And it is the property of the joint density function. If you are integrating the joint density function in the whole domain, its value actually equal to 1. So this should be equal to 1 on the property of joint density function. Okay. Now we come to this one. Since here the limits of the integrations are constant, so you can anytime change the order of integration. Either you want to can integrate with respect to x, or you can integrate with respect to y. Because if the limits of the integration are constants, you can change the order of integration. So here, what I do in this case, since y is there, so I integrate in this instance with respect to x first. And since here x is there, so I integrate with respect to y first. So we'll see. So what I did like this. So I change the order of integration. I take x outside and integrate minus infinity to plus infinity into the joint density function of xy dy. And then later I integrate with respect to x. So, and in the second part, I will write like this: x goes to minus infinity to plus infinity f of xy dy. And once this is evaluated, I integrate with respect to y. And here I written c into 1, not x. Okay. Something is wrong with it. This c multiplied by 1 because this is 1 from the property of joint density function. So if you see what is this one, I am integrating the joint density function with respect to the variable y within the whole domain of y. It means it will give me the marginal density function of x because I am integrating with respect to y within the whole domain of y. So it will give me marginal density function of x. Similarly here, I am integrating with respect to x within the whole domain of x. I will get the marginal density function of y. So I will write like this because it is marginal density function of x. So fxx. Okay. Similarly, this is a marginal density function of y. So fyy. And this is c into 1. So c only. Now, what is this one? If you see, this is the definition of expectation of x because you are integrating x into the density function of x within the whole domain of x. So it is expectation of x. Similarly, it is expectation of y because you are integrating y multiplied by density function of y within the whole domain of y. You will get the expectation of y and 1. So this is the way you prove this result for the case of two continuous kind of random variables. Similarly, you can prove the same result for the discrete kind of random variable. When you are trying to prove this result for the case of discrete kind of random variable, here instead of integration, we are having double summation. And then you can try. Now, we define another term is covariance. So like if we are having two random variable x and y, and we want to know what is the relation between them, then this can be done by this covariance term. Like if x is increasing, whether y is also increasing, or x is decreasing, y is decreasing. So this can be calculated by this term covariance, and the covariance is defined like this: covariance of xy is expectation of x minus expectation of x into y minus expectation of y. So this is the definition of covariance of x comma y. So you have to take expectation of x minus expectation of x into y minus expectation of y. Or if we simplify this, like if I multiply this part with this,
Sir,
I
your
will
screen is
get
not
this
clear.
x. I think it is visible. Is the same problem with the others?
Yes, sir, not visual.
It is Rohit Kumar, not visible. Vishal Jaswal, is it visible to you?
So now, sir, now it's visible. Yes,
Now
sir.
it's
It's
visible.
yes.
Rohit, for you it's not visible. Mr. Rohit Kumar.
Yes, and now it's visible, sir. Due to network fluctuations, this is happening.
Okay. So how we define this covariance? Like if we are having two random variable x and y, the covariance is denoted by this COV x comma y, which is defined by this expectation of x minus expectation of x into y into expectation of y. So if I multiply these two parts now inside this big bracket, so x into y, xy, x expectation of y expectation of x, and expectation of x into expectation of y. So now we use this previous result we proved earlier. This one, the expectation of ax plus by plus c is equals to a expectation of x, b expectation of y plus c. So it means like this is something like this. So I will take this outside expectation to each and every term. So expectation of xy. So here this expectation of y is actually constant because it's a mean already calculated. So here x is only variable. So outside expectation will go to on this, and this expectation of y is treating as a constant. It will be outside of this e. So you are getting second term like expectation of x. Similarly, in this term, expectation of y is constant. So it will be outside of this e, and this e will affect only on this y. So you are having this expectation of y into expectation of xy. And here, expectation of x is constant and y is also constant. So if both are constant, then this term is a constant, and the expectation of constant is the same term. Like you can see now here also, there's expectation of c is actually c. So what if there is no variable, then it's same thing. So here expectation of x is a constant, expectation of y is also constant. So it will remain the same. So here this thing remain the same, and it is in plus, it is in minus, so it will be cancelled out and you are having it like this. And finally this. So some use this formula to calculate covariance between x and y. Another one use this, and I use this one most of the cases, but it is your choice. You can use anyone, either this one or this one. And even though if I ask you in some Viva, like I will ask you what is the covariance of x and y, so you can give any answer. Like expectation of xy minus expectation of x into expectation of y, or you can say like this also. So now this is the one result. Variance of ax by plus c equals to a variance of x, a square variance of x, b square variance of y, 2ab covariance of x comma y. So how we prove this result? Because we know the definition of variance. If you remember the definition of variance of x is expectation of x square minus expectation of x whole square. So this is the definition of variance of x. And here actually capital X is like this, ax plus by plus c. So in this definition, expectation of this square minus expectation of this whole square. So I use that definition of variance of x. Then it is actually square, so I can expand this x square. So this square is ax square, a square, like like x plus y plus z whole square is x square plus y square plus z square plus 2xy, 2yz, and 2zx. So I use that formula to write this, and I will get this one. Ax square by square plus c square 2x abxy 2acx and 2bcy. Now this second part, because it is the square of this expectation, so first I have to simplify this inside part. Okay, like someone may of you, someone may will expand a square here and now, then it will be some problem for him. Maybe he will not get the right result. So first you take this expectation inside because it is expectation of x whole square. So expectation goes inside. You know that today we took this result: a expectation of x plus b expectation of y plus c, and then we have to take square in the next step. So here, if you take the x square, so first because here it's like expectation of this like this. So now as this e goes inside of this, similarly this e goes inside of each and every term here. So we'll take like here a square is constant, so it will be out, and expectation of x square. B square is constant, expectation of y square. C square does not having any variables, so c square. So 2ab is constant, so expectation of xy. Here 2ac is constant, so 2ac expectation of xy. Okay. Then we have to expand this one also. So to get this one, we write this here. Because here like a, first we have to open this square, a expectation of whole square. Okay, this writing practice you should take care. Like some of them and some of you write like this, equal to expectation of x square. Someone x whole like in bracket expectation of x square. Some of you may write like this and they will get 0 because it is expectation of x square here, and it is expectation of x square. Expectation of x whole square and expectation of x square. So you should take care of this thing when you are writing. So a expectation of x square, b a square y square, expectation of y square, c square, 2 expectation of x into expectation of y. Some of you what will do in exam in my from past experience, write this as expectation of xy, and then they will get 0. Or some of may use another notation like e square xy, they will also get 0. Okay, so like expectation of x, expectation of y, and then 2a expectation of x plus 2bc expectation of y, and then to see what can be cancelled here. So you can see here 2ac expectation of x is one term here also, so it is plus, and this one is minus. So this one is cancelled out. 2bc expectation of y is there here also. So this one is cancelled out. And this c square is also here and here also. This one is also cancelled out. So after this cancellation, we are having this one. A expectation of x square, B expectation of y square, C square. Okay, so we written, I think. Okay. So from like after calculation from this line, we directly go to here because this first term is having a square here and here also a square, and it is expectation of x square and it is expectation of x whole square. So I take a square common and I will get this expectation of x square, this term below, not above. This below term I will get the expectation of x square minus expectation of x square whole. Then b expectation of y square, this and this. Here b square is common, I take b square outside. So expectation of y square minus expectation of y whole square. Then 2ab is common. And then here I am having expectation of xy. And here I am having expectation of x into expectation of y. So that's why I'm telling you some of them write this thing as this same and then they cancel out. And then they don't know what to do, what kind of result they are expecting. So then, what is this one? If you remember the definition of variance of x, it is variance of x. Expectation of x square minus expectation of x whole square. What is this? It is variance of y because it is expectation of y square minus expectation of y whole square. And what is this? Today only we define this. It is actually covariance of x and y. So this is the formula like variance of ax plus by plus c is equals to a square variance of x, b square variance of y plus 2ab covariance of x comma y. So today's class is over. I stop here and we will meet again tomorrow. For attendance, today I will give attendance to all of you. Okay. And one more thing, today or tomorrow, I will give you assignment and you submit this assignment before 28. Okay. If you have anything to ask, you can ask, or and